I'll start off just saying 2 cents about the first problem set, which is due a week from today. I've put the questions in Wiley Plus. I'm waiting for them to activate the questions. I don't have full control over it. So as soon as I have the problem set up, I'll put it on Wiley Plus. I will probably write you guys an email saying the first problem set is up. The other thing that 10% of the semester score is associated with just activity on Wiley Plus. And to have that happen, the best way for me to do that is to assign what are called Orion questions. The Orion questions can appear as an assignment, or they can show up as they're part of the reading. If you look on it, there's a tab associated with the reading, and to its right is a tab associated with Orion practice questions. Orion, like the archer. What else? I will probably assign Orion questions for each of the 9 8. I forget how many chapters we'll do this semester. Anyway, whatever they are, I'll assign 20 questions per chapter, and I'll make them do either at the exams, at the midterm, the first and second, and the final, or just at the final. The point of doing those questions is that to learn some of these concepts, you just have to keep facing challenges and not just thinking or listening, reading, listening, and inactively going You have to actually struggle with them. So the more of those I give you, ultimately the better you'll learn the material, I think. So when I write the email, I'll tell you about where to find the Orion questions too. And one thing about the Orion questions is that each time you encounter them, they have a diagnostic, they call it, up front. And the diagnostics look a lot like Orion questions with one exception. Chapter 1 diagnostic questions are nearly all quantitative. They make you calculate things. And I find them tedious myself. And like they're not the kind of questions that I like to ask of students. They're associated with the book, but they're not. Anyway, I will describe in my email, you can blow off the diagnostic questions by pushing a little red circle with an X in it. And it'll say, do you really want to get rid of these? And you can say yes. And then you will never see them again. So, in general, just answering questions is a good thing. And I will use a measure of your doing the questions and trying to get them right as this 10% of the grade. Mostly, you'll all come out with pretty similar scores, so it won't make much difference unless you don't do it. The point is just to give you some short-term incentive to challenge yourself. Any questions about problem set Orion stuff that you can anticipate already? We'll come back to it sometime when you have some clue what I'm talking about. All right. Having said that, then, back to the topic at hand, which is falling balls. And I finish with this slide, but I want to just sort of set the stage again and then finish doing the falling balls. The motion of a falling object is sort of the second simplest kind of motion. The first simplest, the most simple, is just coasting. In the absence of any net force, you just do what you were doing. Simple, okay? Hopefully that now starts to make sense. The falling motion is it's different. It's motion where you're accelerating steadily due to a steady force. The net force is constant. When you let go of a ball and the only force acting on it is its weight, it accelerates in response to that weight. And it accelerates at a certain acceleration. And I talked at some length last time. The acceleration of a falling ball, a falling person, a falling rock, a falling almost everything else that doesn't have to encounter wind problems, air resistance, they all accelerate down at 9.8 meters per second squared, approximately. That is, they accumulate downward velocity at a rate of 9.8 meters per second every second. Doesn't matter what they are. Everything falls together. So it's a steady downward acceleration. Whether the ball is motionless or heading downward already or heading upward, doesn't matter. They're all accelerating downward at this steady this steady pace. Questions about that? It's not a trivial observation, but it's simple, but not necessarily easy to grab hold of and get settled in your head. Okay, well, when you do drop something from rest, from motionlessness, and it immediately begins to accelerate downward at the special acceleration, the acceleration due to gravity, and that means that it goes faster and faster as time goes by. After 1 second, it has accumulated a downward velocity of 9.8 meters per second, because it started at 0, and the acceleration is the rate at which that's changing. The velocity is changing. In 1 second, it changes by a total of 9.8 meters per second downward. After 2 seconds, it's accumulated yet another 9.8 meters per second downward. It's up to almost 20. It was too bad that the acceleration due to gravity isn't just dead on 10 meters per second. So it's much simpler to talk about. And sometimes I'll just sort of do that, approximate it as 10. So it goes, first second it goes to 10 meters per second. Second second it goes to 20 meters per second. Third second it's going 30 and 40 and 50. It just keeps on accumulating more. Okay? Eventually, when it goes real fast, air resistance becomes a problem. That's an interesting story, but it's not the subject for this semester. When you go into air resistance, if you're falling, you jump out of an airplane, and you're falling downward, there's this tremendous wind coming up at you, and that pushes on you. And so you aren't truly falling anymore. You have more than one force acting on you. You got your weight, but you also have this air resistance force blowing you upward. All right? But if things aren't falling for very, very long, they don't go very fast, that air resistance isn't so important. All right, so this gradual increase of speed, it's steady. Well, how far the ball falls, which is where I sort of finished off last time, was it's covering more and more distance with each passing second because it's moving faster in the downward direction. And that's why, as I have shown up here, in the first second it only falls about 5 meters because its average speed during that first second is pretty slow. It started the second motionless. It finished the second heading downward at almost 10 meters per second. On average, it was only traveling about 5 meters per second during that first second. It only covered 5 meters. Second, however, it was going faster on average. Why? Because it started the second already moving downward at 10 meters per second, and it finished the second traveling twice that fast downward. So its average downward velocity during the second is 15 meters per second almost. So it covers more distance. The third second, it covers more distance still. So one of my favorite questions to ask on exams and stuff like that is you drop something for a couple seconds. Let's just pick a number, 4. You drop it for 4 seconds. At the 2-second point, you dropped it from rest. 2-second point, sort of where is it compared to the start of its fall and the end of its fall? Well, it's much closer to the start because that first 2 seconds, it just doesn't move very fast. In fact, it's only made a quarter of its trip. It's in the second 2 seconds that it makes the remaining 3/4 of its downward journey. And that's why I was going on waxing poetic about bungee jumping. It's easy to make a bungee jumping system where you fall for a couple seconds, 2, 3. Sorry. Life at universities and stuff, you collect all kinds of lovely germs. Yeah, so it's 2 or 3 seconds of fall. You don't travel very far. I mean, you travel a considerable distance, but not super far. But if you try to fall for 6 or 7 or 8 seconds, oh my gosh, real trouble. You travel so far, it's very hard to do that. The only case where they do actually allow things to fall for many seconds, tens of seconds, is the famous, well, I know of it as the Vomit Comet. These planes that travel in the arcs of a falling ball, actually. And they filmed, for example, Apollo 13, that movie, where they're trying to make people weightless. Well, it's a long story about weightlessness is the same as falling. In any case, if you move up and down thousands of feet, as you can do in an airplane, you can actually fall for tens of seconds. All right, to reel myself back in, the story then is just that this constant downward acceleration When you drop something from rest, it goes faster and faster downward, and it covers bigger and bigger distances every second. Any questions about that? Well, that then brings us to sort of the next possibility, which is what about when the ball is going upward? So the story doesn't start until it leaves my hand, and suppose because while it's in my hand, I'm pushing on it, and it's not just experiencing its weight. After it leaves my hand, it goes supposedly straight up. Suppose I throw it really hard, and it rose for 3 entire seconds before coming to momentarily to a stop. Well, in that case, it's still accelerating downward at 9.8 meters per second squared. Same as always. And what that means then is it starts with a large upward velocity given to it by me, and it gradually loses that. And you could say it's decelerating, which is, again, that's just a piece of jargon that describes a particular type of acceleration, namely one in which the acceleration is in the direction opposite the velocity. So the thing slows down. So in this case, the ball, because it's heading upward and accelerating downward, is accelerating opposite its velocity, and it's slowing down. So it starts at almost 30 meters per second. So this actually takes a pretty serious throw. After 1 second, it has lost 10 of those meters per second. It's only at 20 meters per second upward. Third second, it's only at 10 meters per second upward. And at the end of the third second, it has momentarily dropped to velocity 0. So it's slowing down. And you can, this is real familiar. This thing goes slower and slower, and at the very top, it's not moving at all. But only for an instant. So, any questions about that one? I'll keep asking you for questions, but you can keep on keeping the code of silence going. All right. Still, the acceleration is still downward, 9.8 meters per second. We're using the shorthand of motion along one direction, which is to use pluses and minuses as direction. So minus means it's a downward acceleration. All right, and the last tidbit in this story is that the rise of the ball, it makes a lot of upward progress during the first second because it was traveling fastest during that first second. The second it doesn't make travel as much distance because it slowed down. Third second, it makes much smaller increase in altitude. And at the end of the third second, it's finally completely lost its ability to go upward anymore. And it's about to go downward. And once it starts to go downward, it's just like a falling ball dropped from rest. Same physics. Indistinguishable. All right, so that's the story of balls going up and down vertically and nothing else. And I think that brings me to a question. Yeah. So suppose it's you that's the falling object. You're on a springboard at the aquatic fitness center. And you go off the springboard, you actually head upward first. That's the point of the springboard, is you don't actually just simply walk off and drop. You actually start the story going up. And so suppose at the peak of your upward trip, the peak of the jump, I guess, is a little vague. It's when you reach the peak of your trajectory, your velocity, and we'll neglect any, actually we don't even need to neglect it. When you're at your peak, what's your velocity like? What's your acceleration like? So you okay with the question? You're at the peak. You're the ball. Now, at the peak, what's life like for your velocity and your acceleration? How many think your velocity is changing, but your acceleration is constant? Okay. How many think B, your velocity is constant, but your acceleration is constant? Okay. How many think your velocity is constant, but your acceleration is changing? And how many think that your velocity is changing and your acceleration is changing? Okay, with the exception of D, there's a lot of voting for A, B, and C. There was no distinct winner in that group. Although I will tell you the answer is among those A, B, and C. So, we'll discuss it among yourselves for the next 60 seconds, and then we'll vote again. Convince your neighbor and the other acquaintances, your frenemies, I don't care. that your answer is right. Oops. All right. We'll come back in. We'll hope you made good plans for the weekend. So the question remains, at the peak of your trip up, when you're the ball, at that peak, tell me about your velocity, tell me about your acceleration. How many think A, your velocity is changing and your acceleration is constant? Okay. How many think B, your velocity is constant and your acceleration is constant? Okay. How many think C, your velocity is constant and your acceleration is changing? All right, we've got a few lingering people voting for C. We're down to A and B, and it's about even still. And I'll give you one more hint, and I'm going to have you struggle with this one more time. If your velocity is constant, and the next second, suppose your velocity is constant, and a moment later, your velocity then is the same as it was now. And a moment after that, it's the same as it was now. Let's see how to do this. Think of the moment before and after the peak. I forget what I just said. It wasn't heading anywhere. Think of I'll just say random stuff. Think of the moment before and after the peak. What was the ball doing just a little before it was at peak? Think about its velocity and think about its acceleration. And think about its velocity and its acceleration a little bit after the peak. What's it doing? And then think, right at the peak, does your previous vote make sense or not? Velocity constant, velocity changing. That's the only difference. You're all agreeing that the acceleration is constant, and that much is good. You're struggling over whether the velocity is constant or changing. Think about it again. 30 seconds this time. You've already planned for this weekend. All right, here we go. We're down to A and B. How many think your velocity is changing, but your acceleration is constant? How many think your velocity is constant, but your acceleration is constant? You finally got it. It's A. Your velocity is changing. I know there are a few people going for this B. Your velocity is changing. Even at the peak, your velocity is 0. For that moment, but just prior to that moment, your velocity wasn't 0. You were heading up. You were still going toward the peak. And just after the peak, your velocity is now downward. You're beginning to descend. So right at the peak, your velocity is 0, but it's still changing. You're smoothly going from heading upward before to heading downward after. And in the past, sometimes it's been helpful to just plot a graph. Okay, I usually don't do numbers and all that stuff. But suppose this is your velocity, v for velocity, and this is t for time. So we're watching time go by. As you head upward, your velocity is upward, and the simple-minded convention is upward velocity is a positive amount. So your velocity, when you left the board, was positive. It was up here, the first instant of time. But because you're accelerating downward and you're accelerating steadily, as time goes, your velocity is decreasing, decreasing. And we pass through velocity 0 smoothly. Nothing special happened at that moment. This moment, when you went through 0 velocity, prior to that you were heading up, after that you're heading down. That's the peak. That is the instant, if I plotted position or altitude as a function of time, right at this time, when your velocity hits 0, you also hit peak height. And you know the old slopes and stuff, it's still sloping down because that's the slope is the acceleration, and you go right through 0. Yeah. Is that okay? Questions about that? Yeah, I'll say yeah. I think I've done my job with that one. All right. I will remind you this question. We did this question. You guys got it right. That on the way up the ball, is anything pushing the ball up? I'm neglecting air. And the answer is no. It's going up because that is its nature. That's inertia. And it's trying to do what it was doing. And in the absence of gravity, it really would keep doing what it was doing. It would go just off forever, head across space, go visit the stars. But because there is gravity pulling down it doesn't coast. Instead, it's accelerating downward. It's slowing down on the way up. It momentarily comes to rest there at the top. At that instant, its velocity is 0, but it's still accelerating downward. So that velocity is changing with time. Okay, we just did that. And then it comes on back down. That leaves one last part of the story. So I've talked about motion along this sort of railroad track, this vertical railroad track, up, down, positive position, negative position. What about if it's traveling in some more complicated direction, like this? In that case, remarkably, the motion of a falling ball separates cleanly and beautifully into 2 parts. This happens occasionally in physics, actually fairly often in physics, when you have only, for example, one force that acts only, in this case, vertically. That force affects the vertical motion of the ball. But there's no horizontal force, nothing else around. And so the horizontal aspects of the motion, what are called components, the horizontal components of the motion are unaffected by gravity. They are the motion of coasting. So a ball that's thrown at some angle is doing 2 separable activities. Vertically, it is falling. It's doing the usual accelerating down at 9.8 meters per second squared trick. Horizontally, though, it's just coasting. It's covering equal horizontal distances in equal times. And technically, you would say its horizontal component of velocity is constant. The details of the mathematically separating out that you can, in this 3-dimensional world, you can pull out the vertical motion and rip it free of the horizontal motion. It's, we can get lost in that. I can get lost in that. I don't, yeah. But are you okay with the idea that the horizontal motion is that of coasting? So this arc that you see consists of two parts. I have videos around. Gosh, what are the chances that I left it on the system here? I did leave it on the system. The ball. There it is. I filmed this online class some time ago. Photograph of that. Where's he throwing it? I was filming 3 guys over at the AFC shooting baskets from like half court. And they were hitting them most of the time. I thought, oh my gosh, it's amazing. So you don't get to see this guy. If I roll back far enough, you'll see him hit it. But they're just hit, swish, swish, swish. You could put me above the basket and let me drop it, and I'd miss. So what this drawing is showing you, it's showing the path. Can you see those dark dots? Those are the basketball completing its arc. Let me dim the lights. Okay, we'll go off. Of course, I leave the key lights that I can't go after. I can get them. There. So he's just completed the shot. There he goes. Flop. And the point to show you is the horizontal motion, which I've ticked off equal times. They're frame by frame, the video camera was capturing frames at equal times, and you can see the spacing between those horizontal lines is just steady. They're getting a little closer together over here on the right, or seemingly so, because of just the vantage point. It's getting farther away from me, the camera guy. Okay? But they're evenly spaced. At the same time, the vertical lines are showing you the height of the ball. And initially, the ball is moving upward quite fast. He's just thrown it, but it's going fast, fast, fast. Slower, 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 slower. Almost not rising at all, then faster, 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 faster. Okay, so the point of all this is to show you that what I've just claimed is real. The horizontal motion and the vertical motion separate beautifully. The vertical motion is that of a falling object. The horizontal motion is that of a coasting object. And the world is, there's so many ball sports. Let me just, I'll get the lights approximately on. Now I've got to fix all the messy things I've done. That'll do it. So all these ball sports, in the absence of air, which is not a trivial thing for many ball sports, the ball is traveling these arcs. They're coasting downfield. At the same time, they're rising to a peak and descending in the motion of a falling ball. All right? Any questions about this stuff? I mean, pieces to throw in here. If you want the ball, suppose you can only make the ball go so fast. Which way do you aim the ball to make it stay, for example, in the air the longest, above the ground the longest? Straight up is the choice then. If you want the ball to take as long as possible to land, put all the speed into the vertical direction. So the vertical upward and downward, the falling motion takes as long as possible, and the ball rises to the greatest height possible. This is often important in sports like, I'm thinking football, punters want to have the ball stay up there as long as possible. It's not necessarily, they don't necessarily want it to go downfield all that far. I mean, yeah, they'd like that too, but they probably want hang time, especially. So they go up a lot. Again, if you want it to cover distance downfield as fast as possible, and you can only throw it so fast or kick it so fast, what do? Go as close to the horizontal as you can tolerate. It will not stay up very long, but it will make progress downfield very fast. And so certain throws where you're passing the ball from in this sport from one person to the next, and you wanted to get there fast, you put all your speed into horizontal motion pretty much. And then if you want to make maximum distance, suppose that's the goal. You want to actually go, you want it to figure out how to get as far away from you as possible. If you don't go straight up, because yeah, it'll be in the air for a long time, but it'll hit you on the head. That doesn't count as much distance. And you don't want to go horizontally because it'll go really fast downfield, but it won't stay up very long. It'll hit the ground almost immediately. It's the 45 degree. It's the best compromise in the absence of air for distance. At that point, you're putting enough of its speed into the vertical motion to keep it aloft for a while, and you're putting enough of its speed into the horizontal motion to make it use that time efficiently to get downfield. Okay? Any questions about sort of balls and trajectories of balls? All right. That, I think, will do it for the world of balls. So, at this point, it's time to bring yet another force into the story. So, with falling balls, the first named force showed up, and that's gravity. The force due to gravity, also known as weight. Ramps is going to bring another force into play, and it's a force. It's got a couple different names. I call it support force. You may have encountered it before as normal force or contact force. It doesn't matter. They're the same thing. And just to give you a preview of what is it, well, if I just let go of this thing, of course, it drops. Right? It falls. It's experiencing only its weight. If I put it on the table, it can remain motionless, meaning the net force on it is 0. Its weight didn't disappear, and yet it's not falling, so it must have a second force acting on it. And that second force acts in which direction? You show me with your hand. And how strong is that force? I mean, this is hard to do. Show me with your hand how far. It's about this strong. It exactly cancels the ball's weight. And it's exerted by an object. It turns out forces are always exerted by something. You ought to be able to name. If the question comes up, and it will, is there a force acting on such and such? Forces are always exerted by something. So you should be able to name what the something is exerting the force. So actually, to go back to this previous question, is there an upward force acting on the ball as it rises? Well, name what's exerting it. It's sure not me. I'm not touching the thing. Voodoo force, right? There's no object exerting the force, so it can't be there. The air actually is touching it and therefore can exert a force on it. So that's why it has an outlaw air. Anyway, come back here. The bowling ball is experiencing a force exerted by something. It's the table. The table's pushing up on the ball. Remarkably, it's pushing up exactly the right amount to support the ball's weight. And that upward force the table is exerting on the ball is called a support force. Interestingly, the ball is also exerting a force on the table. Happens to be in the downward direction. It's also a support force. But that's part of the story in the future. All right, so how did I... There's a question here. I must have deleted the question. I like the question. I have to go find it in its reappearance. Sorry. Oh, man. I've got the version without any questions in it. 1 second here. Plan ahead. Question, yay! All right, I'm easily pleased. Can a ball ever push downward on a horizontal table with a force that's greater than the ball's weight? So I already just talked a little bit about this ball is being pushed up by the table with a force that exactly cancels the ball's weight. And it shouldn't be too surprising that right now the ball is consequently pushing down on the table with a force that's equal to the ball's weight. If that weren't the table, that were your hand, you would feel that you're pushing and that it's pushing back. So familiar? But is there a circumstance in which the ball can push down the table with a bigger force than that, bigger than its weight? So this ball is a 16-pound bowling ball. Can it ever push down on the table with a force of 1,000 pounds? You okay with the question? Is the ball at rest? I didn't say anything about the ball's motion. So the answer is not necessarily. It's not necessarily at rest, which should be a useful observation. Thank you. How many think that it can push down with a force larger than its weight? Ooh, how many think not? Ooh, you guys all figured it out. How can I make it push down with a force greater than its weight? Say 1,000 pounds. Falling, drop it. During that impact, dust came up. That was kind of cool. Yeah, I think I came out of the cracks between the boards. Yeah, the force, that peak force was easily in the 1,000-pound range. The physics behind that is actually pretty, it's important. It's stuff that you need to know. It's like, where did that come from? The ball, once I dropped it, it did what we've talked about up until now. It accelerated downward at 9.8 meters per second squared, faster, 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 faster. At the moment it encountered the table is looking at it going like, I'm here. You may not come where I am. That's the origin of a support force, is the atoms and molecules do not like to overlap in space. And they push ferociously against each other, given the opportunity to, no, table, just, no, you may not come here. And so the ball, however, has a downward velocity. And the ball is determined to keep doing what it was doing. It's inertia, after all. It's going to go down, and the table has to say, no, 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 I'm going to push up on you to slow you down, to make you accelerate upward and bring your velocity to 0 as quickly as I can so that you do not get deep into me. And in a small fraction of a second, maybe a hundredth or even less than a hundredth of a second, the table pushes so hard on the ball that it removes all that downward velocity. It accelerates it upward very fast, enough that the downward velocity goes from, 2 meters per second. I don't want to even go close to 10 meters per second. 2 or just 1 meter per second to 0 in a couple thousandths of a second. That very rapid change of velocity requires an enormous acceleration, because that's what acceleration is, after all. Acceleration is the rate at which velocity is changing with time. So to change velocity quickly, you have to have a big acceleration. To have a big acceleration, you have to have a big force, particularly when the mass that you are accelerating, in this case the bowling ball, is big. That bowling ball it has a lot of inertia to it, as measured by its mass. It does not like to stop. And so the table has to push up with a force of 1,000, 5,000 pounds, something like that, to bring the ball to rest in a tiny fraction of a second. In fact, it didn't even bring the ball to rest. If you notice, the ball bounced, which is itself interesting physics for the fall, of course. The ball actually ended up heading upward. I'm not going to do it again. I've been breathing enough dust already. So that kind of force where two surfaces hit and they push ferociously on each other in order to avoid overlapping in space, those are called, just to give them a jargon name, impact forces. And they're really useful for things. When you want to pound a nail into a wall, board or something like that, if you try to push a nail into a board, you can't do it with your thumb. You can't even do it with a hammer if you just push. But if you get the hammer moving and make it encounter the nail while the hammer's moving fast, the hammer and nail will go like, well, no, we can't occupy the same space. Slow down, go the other way. And they'll push ferociously on each other. And the force that the force that the nail exerts on the hammer will stop the hammer's motion toward the nail. But at the same time, the hammer will exert a force back on the nail that will push the nail so hard it will push it right into the wood, at least a certain distance. Can you follow that idea? So impact forces, pay attention to the world around you. You'll see lots of them showing up. It's a piece of one of my favorite harangues, which is when you're wandering around in the middle of the night, desperate to go get that, I won't use a brand, the candy bar that you know is on top of the fridge, and you walk bang right into the wall, right? Big impact force if you hit the hard wall, cement cinder block wall in your dorm, because the change of velocity is so fast, it involves huge forces. You do much better to walk into that big plush toy that your roommate won at the fair, woof, and you bounce off of it, and you go, safe. Because you still didn't overlap in space for any length of time, significantly in space. But the transition from moving fast to not moving, or maybe even moving backwards, was so slow, it involved small accelerations, and therefore small forces. So that's why, that's a way of seeing why we go through life trying to avoid rapid accelerations, because they involve big forces that hurt. You like to hit things that are soft. You don't stub your foot against the cement, you stub it into, the couch. And it bounces. It doesn't hurt as much. All right? Sure seems like it's related to ramps, but we'll get there. Okay, so some observations about ramps. The reason support forces are going to be useful is because motion on a ramp involves the ramp surface and whatever's moving on the ramp, they're pushing on each other, and they're pushing with support forces. They may also be pushing with frictional forces, but that's a different topic. And to avoid the frictional force issue, I use a little wagon, my little toy wagon here. So frictional forces are pretty minimal, but this wagon is held up right now by support forces exerted by the ramp. It's not a very rampy ramp right now, but it'll get there. All right. So some observations about ramps. It's difficult to lift something really heavy. I don't know. In the book, it's a piano. You try to go straight up with a grand piano or something like that. This involves exerting a very large force on the piano. If you want to move the piano up at constant velocity, so this is the piano. It's a round piano, newly engineered. This is what the suits in the office designed as the piano. Whatever. Going straight up is tough. It involves exerting a force. If I go up straight up at constant velocity, I have to support the ball's weight. So I have to push up with a force that's equal to the ball's weight. It's in the upward direction. It's a pretty big force in this case. It's like 16 pounds, and up we go. You can do that, but if it were a 200-pound or 400-pound piano, you couldn't anymore. That's just too heavy. So what do? You use a ramp. And a ramp allows you then to get that same very heavy object up to significant height. And you're not getting something for nothing. You're exchanging certain features about the motion to do it. But it is the case that the ramp is helping you support the weight of the piano or ball. And we'll see how that there are trade-offs and what the trade-offs are. You know from experience that different ramps have different. All ramps make it easier to get something up to a certain height because it involves less force. But the amount of force you have to exert on say, a piano, rolling it up a gradual ramp, is less than the force you have to exert on the piano to roll it up a steeper ramp. So the steepness of the ramp matters, and we'll see why that's the case. All right. So the questions that I'll go through in dealing with ramps, these 5 guys here, and the first of which is the story of the support force. Why doesn't a wagon, so I'll gear it towards a wagon rather than a piano, so it's this guy. Why doesn't the wagon fall? And this ramp right now, because it's reduced to just flat, we can pretend it's a sidewalk. And so, what's holding up the wagon, preventing it from falling? So that's my first story. And it's just the sidewalk pushes up on it. And it comes about microscopically because there are atoms and molecules at the bottom surfaces of all 4 wheels and the handle. And the sidewalk similarly has atoms and molecules there. When you try to shove those atoms and molecules on top of each other so that they overlap, and the details are significantly, there's a lot of science in the details, but I will sweep them under the rug. As they overlap more and more, they push apart more and more strongly. So it's very hard to get the wheels and the sidewalk to overlap significantly in space. They will push just very hard against one another. And those forces that the sidewalk is exerting on the wheels and the wheels are exerting on the sidewalk, they're both exerting support forces. Some story about support forces. Support forces, because their purpose is to prevent overlap, they act exactly perpendicular to the surfaces that exert them. So, for example, this stick is now being supported by the table by way of support forces. And if I get my hand out of it, it's pretty much none at all. The table's support force is straight up along that stick. It happens to be along that stick. It's straight up, not because the stick is straight up, but because, so I'm just using the stick to illustrate the direction, because the table is horizontal, and the line perpendicular to a horizontal surface, if you don't remember what perpendicular is the generalization of right angles. It's straight up. It's right angle in every respect. So the support force from a horizontal surface has to be straight up. The support force from a vertical surface, like the walls, is horizontal and straight at me. So if I go try to walk through the wall here, bang, it stopped me by way of a support force. In this case, the support force was perpendicular to the surface, perfectly horizontal to your left. Is it okay? You might wonder, what about forces that aren't exactly perpendicular to surfaces? They do exist. This thing, as I scoot it around, is experiencing forces along the surface that slow it to a stop. Those parallel forces are frictional forces, and we're going to save them for a while. So the support forces are perpendicular. The frictional forces are the other possibility, the parallel. And you can mix the two and get any angle you like. So between support forces and frictional forces, you have the whole set of what's possible in the way of forces that surfaces exert on one another. All right. You okay with support forces? Okay. So that then raises a question. The sidewalk is pushing up on that wagon with just the right force to support the wagon's weight. We know that because the wagon's not accelerating. It happens to be, it's motionless and staying motionless. So we know that the net force on it is 0. So this is the logical process. I'm giving the full legal argument for why I know that the upward support force on the wagon is exactly equal to its weight, but in the opposite direction. The whole legal argument, like, in a court of law, judge, I know it's exactly equal because the wagon's got net force 0, and I know that because it's not accelerating. Okay? So I know that its weight is downward, a certain amount. The sidewalk has to be pushing upward with the same amount. They cancel perfectly. That's certainly true, just by observation. The question is, why? Why is the sidewalk pushing just right? And it turns out, and this is one of these questions that I think went through my mind when I was your age in a normal physics class. It was sort of never addressed. Like, it just never came up. But it's actually kind of, well, it doesn't have to be. We've seen that it is possible for the sidewalk and wagon to push very hard against each other. All I have to do is do this. And I can break the things. So they happen to be pushing just right. And ultimately, the way in which they figured out how to push just right is they negotiated. There was actually when I set the wagon down, there was a little bit of a bouncing process as the wagon and the sidewalk tried to figure out how hard do they have to push on each other to just have the wagon sit there. And you can't see that negotiation process very easily with the wagon by itself. But let me replace the wagon, the sidewalk, with a spring scale that reads how hard it's pushing. This, if I push on this, it's pushing up on me with a force of 40 newtons. It's a strange scale, it reads in newtons. 40 newtons. Now it's pushing with 80 newtons. It's really telling you how hard it's pushing on my hand. So if I put this heavy block in the wagon and set the wagon on the scale and just get everybody all happy, the scale is telling you it's pushing with 59 newtons of upward force to support the weight of the wagon and the weight, and the block in it. But watch what happens during the process of putting it on there. The wagging tail trick there, that the scale pushing different amounts, that's real. The scale was trying to figure out how hard do I have to push. If the scale pushes too weakly, not enough push, then there's the net force on the wagon is downward. Its weight is not fully supported, so it accelerates downward and eventually begins to move downward and dent the scale deeper. So if the scale under supports the wagon is going to eventually start heading downward and smush the scale. If, on the other hand, the scale pushes too hard, it pushes upward more than the weight of the wagon, the wagon will accelerate upward. And eventually the wagon will begin to move upward and leave the scale. So the negotiation occurs as the scale and wagon push too hard, too soft, too hard, too soft, too hard, too soft. And eventually they settle down at just right. Goldilocks shows up. And I'll finish that thought on Friday.